Hi everyone, we've come to chapter 2, Properties of Pure Substances. Now, chapter 2 covers the basics of thermodynamics. The basic as in you definitely need to master chapter 2 in order to have a chance at chapter 3, 4, 5, 6, and 7. Okay, so it's very important that you understand everything that is happening in this chapter, right? Now, here in this video, we will talk about phases. Okay, what are phases? And phase change processes. Okay, so I think you've learned about processes in the previous chapter. So today we're going to look at phase change processes. Okay, and the rest of this chapter is about property diagrams, which we'll do in the next video, maybe next week in week 2, and also property tables. Okay, now just a reminder, please download a copy of the property table before the next video. If you're able to print it out, that's even better. Okay, but if you can't print out, you can just have it ready so that it's already open when you want to watch the video. Okay, pure substance. The definition of pure substance is it's a substance that has a fixed chemical composition throughout. All right, so here we have two examples of a pure substance. On your left, you have nitrogen gas. Nitrogen gas is a pure substance because it's made of only nitrogen atoms. No other substance inside here. Okay, but air is a bit special because you know the air is made up of many types of gases. Okay, there's nitrogen, there's oxygen, argon, etc. There's even water vapor inside it. But why do we treat it as a pure substance? Because it is naturally occurring. You can find air anywhere and easily, right? It's naturally occurring and commonly found. Basically, everywhere you turn right now, there's air, all right? Unless the place has been turned into a vacuum, and there's no air. Now, let's look at this difference, these two different diagrams. Okay, on your left, you have H2O. H2O is water, and inside this system, you have water in liquid form, and also at the top, you have water in vapor form. This is something like when you want to boil water, you have the liquid at the bottom and the vapor starts to rise. Okay, so this is first example. In this example, this is a pure substance, because even though it exists in two different states, this is vapor and this is liquid, but it is still pure H2O, so it's a pure substance. On the other hand, when you have air, let's say the air, the top part is still gaseous, and then some part of it condenses into liquid, it no longer becomes a pure substance. Why? Because the part that turns into liquid is the H2O part that's inside air. Okay, it's not every component turning into liquid. There's no nitrogen or oxygen or argon in here. Okay, this is only H2O molecules. The other gases remain at the top. So this is no longer a pure substance. Okay, so let's look at the phases of pure substance. The phases that you know now, I'm sure, would be solid, liquid, and gas. Okay, so in thermodynamics, we are focusing on liquid and gas. And because of that, we are breaking them down into 5 phases. So between liquid and gas or vapor, we are going to have 5 full phases, right? And these 5 phases are going to follow you until chapter 7. So, okay, this part is a little bit more intense. So please focus. You can rewind the video, you can pause, you can watch it again at another time, right? But please understand the whole part. Phase change processes of pure substance. Just think of it as a boiling process. Okay, you are applying heat into a closed system and we are observing what happens to the content of the system. Okay, so the system in question is a piston. Okay, so this is a piston. We have a certain mass of water inside. It starts at 20 degrees temperature and the pressure is 1 atm. 1 atm is about 101.325 kPa. So it is basically atmospheric pressure, right? This is atmospheric pressure. So normally we call this water, okay? And specifically, it's a liquid form, okay? Because water can be vapor and solid, but this is liquid water. But in thermodynamics, we're going to call this compressed liquid. Okay, compressed liquid. Why compressed? Because it's a substance that is not about to vaporize. If you just leave it like that, it will not turn into vapor. It will stay as liquid. All right. So at atmospheric pressure and 20 degrees, water exists in liquid phase or compressed liquid. So heat is applied. All right, and we can see that it's starting to change. This is you boiling water, remember? So the temperature will start to increase from 20 degrees. It will start to increase until it reaches 100 degrees. And of course, the pressure is still the same because you're still boiling water in atmospheric pressure. So P remains 1 atm. Right? Now, this state is called saturated liquid. Why saturated? Saturated means it's full, right? So that means this state is full of liquid. It cannot have any more liquid. Saturated liquid is a liquid that is about to vaporize. If you put any more heat, there won't be more liquid, but there will be vapor instead. Okay, it will start to vaporize if you continue this process. So let's continue this process. Okay, this is when steam starts to form or vapor. This is called a saturated liquid vapor mixture, the state at which the liquid and vapor phases coexist in equilibrium. Okay, now one important thing to note is that of course the pressure remains the same because you can see that the volume has expanded. Okay, because the steam is taking up so much space, the volume expands. That's why the pressure remains constant. And the temperature also remains constant. So that is interesting. Okay, even though heat is being applied, the temperature is constant because all that heat is used to change the phase from liquid at the bottom to this vapor. As more heat is transferred, part of the saturated liquid vaporizes. And what if you continue heating? Okay, if you continue heating, it will reach a state of only vapor. Okay, this is called saturated vapor. So it's the opposite of saturated liquid. Saturated vapor is a vapor about to condense. That means if you, at this stage, you remove the heat, it will straight away start to condense, turn back into liquid water. Okay, it's full of vapor at this point. All right. At atmospheric pressure, the temperature remains constant until 100 degrees, until the last drop of liquid is vaporized. So understand that this state, state 4 here and state 2 are instantaneous states. That means you can't linger at this state for a long time. Okay, here it can be going on for a long time, and then once it reaches state 2, if you keep heating it up, it will straight away cross to state 3 until everything is vaporized, and then it will go through state 4, this which is also an instant. And after that, if you continue heating, what happens is the vapor will turn into superheated vapor. So that is the final state, and you can see that the volume has increased greatly, okay, even compared to the saturated vapor phase. So in this state, while the pressure is the same, the temperature is allowed to increase. So compare this vapor and this vapor. Okay, this is vapor that is about to condense, while this is a vapor that is not about to condense. Okay, it will remain vapor until it reaches this temperature before it starts to condense. when you remove the heat. Right? So those are the 5 phases of pure substances. You can repeat this video, you can look at the lecture notes and view it at your own pace, or you can also look for other resources if you want. If you have that textbook, you can read about this. Okay, another part related to the phases of pure substance is the process diagram. Okay, so here we're going to show what you saw earlier in the previous slide on this TV diagram. So on the TV diagram, first you have to draw the axis. Okay, it will be useful if you have a piece of paper and a pen now to try and sketch this yourself, yeah, because you have to sketch diagram whenever you answer assignments and tests and final exam. So it will be great to start practicing now. So the TV diagram has temperature on the y-axis and volume on the x-axis. In state 1, it starts as compressed liquid. Okay, so you can just mark it anywhere in the slightly lower volume region and lower temperature region. As you know, the temperature is 20. Okay, now we heat it up and it starts to become saturated liquid. Note that there's a slight change in volume. Okay, only slight. And the temperature has increased significantly to 100 degrees. So that's state 2. Next is throughout the vaporization process. Okay, while the liquid is vaporizing, we have constant temperature, if you recall. Okay, 100 degrees the whole way. And the volume is increasing greatly this time because this is a liquid and then it's increasing all the way until it reaches saturated vapor state. Yeah, this is the vapor state that is about to condense if you remove the heat. Okay, so this is saturated vapor and finally superheated vapor. Big change in volume, big change in temperature. So this is 100 degrees. Here we have 300 degrees. So all these 4 states can be shown in a continuous line like this. Please forgive the wonky lines. Okay, so this is a nicer version of it. So learn how to draw it yourself and then refer to this diagram. So what I want to point out here is that all these are happening at a constant temperature of 1 atm or atmospheric pressure. Okay, so because of that, we call this line a constant pressure line. Okay, and it's not only 1 atm that you get this line, right? You will see that in the next videos. Okay, now it's important to understand saturation temperature and saturation pressure at this point. Okay, once you've seen the process diagram. So if you remember from fluid 1, we've talked about saturation pressure, which is P sat or boiling pressure, and saturation temperature is basically boiling temperature. Okay, now these two depend on each other. If temperature is 100 degrees, the boiling pressure is a certain point. It's fixed. If the temperature is 10, the boiling pressure is also a fixed value. And that whole list can be found here. This is just part of it. Okay, and a certain temperature will give you a fixed P sat, and a certain pressure will give you a fixed T sat in return. Okay, so they are related. So for example, when temperature is 100 degrees, P sat is 1 atm. But if you change that, if you say pressure is 1 atm, then the T sat or boiling temperature is 100 degrees. Right? Okay, those are just the definitions. Now, how do we put all that information on the process diagram? So this is the basic diagram that you saw earlier. This is for 1 atm, remember? Now, when you have other pressure, but you want to draw it on the same diagram, all right, we get this. Okay, so you see the lower the pressure is, the lower the position of the constant pressure line is. Okay, but you can see that they look similar. They have a slope here, steep slope between compressed liquid and saturated liquid, and then horizontal line, lower pressure, longer line means longer boiling process, longer vaporization process, and then this is the superheated region. Okay, and it's useful to add this line. So this is a bell-shaped curve which helps to sketch the process. So first, when you draw the TV diagram, it's useful to draw the bell first. All right, so we are going to discuss more about this in your virtual class. And in the meantime, please note down all questions, whatever that you don't understand, whatever that's not clear. Okay, so that we can have a more efficient virtual class. So let's recap. What you've learned in this video is definition of a phase. Okay, you know what phases are. The 5 phases of pure substance, you've learned about that. Please go back to that part and make sure you really understand. P-set and T-set values, what are they? And also you have learned about, you've learned how to sketch the property diagram, the basic one at least. All right, so as a reminder, please download a copy of the property table. We'll be using them a lot in the next videos. Okay.